Hi everyone, Miss Mazen here. Today we're looking at quadratics. We're going to do a quick introduction and then go over the transformations possible and how to graph them. That's the MPM 2D Grade 10 Academic Math. What is a quadratic function anyway? It's a U-shaped graph, kind of looks something like this. And it's also referred to as a parabola or curves, okay? There's three ways to identify it, which we're going to look at shortly. And there are three equations associated with parabolas: standard form, vertex form, and factored form. And we should also note that h and k in the vertex form is the highest or the lowest point of your parabola, so it's called your vertex. And r and s in your factored form are your roots, also known as your x-intercepts, or where your parabola hits the x-axis. So here are the three ways to identify a quadratic relation. It's by t-chart, by graph, or by equation. So if you're working with a table of values and your second difference is the same, then it's a quadratic relation. Here's what I mean. Here we have a table of values. Looking at our y values, we can calculate our first difference. So that's 1 minus 0 is 1, 4 minus 1 is 3, and so on. Our first difference does not give us a consistent number, so we know that it's not a linear function. Now, to take it one step further, we're going to do the same thing with the results from our first difference to calculate our second difference. 3 minus 1, 5 minus 3, and 7 minus 5 will give us our second difference. All of those values are the same, which means that this is a quadratic function. Now, by graph, super easy. It's a curved line or a U-shaped graph. Also known as the parabola, so it's U-shaped. That's pretty much a visual representation of a quadratic function. And for equations, in your equation, the highest power is 2. If you have x to the power of 2 in your equation, and that's the highest one, then it's definitely going to be a quadratic function. And it can be represented in any of these formats, so long as the highest value or the highest exponent is 2. Now let's take a look at the properties of linear functions and those of quadratics. Now, if you're comfortable with working linear equations, you'll see that quadratics is much of the same. Let's get into it, starting with the parent graph of each. Y equals x is the parent graph for linear functions, and we know that that's a straight line, and y equals x squared is the parent graph for a quadratic function, and that is a U-shaped graph. Okay, now everything that you've learned so far about linear functions, y equals mx plus b, is just a variation of the parent graph, y equals x. That same rule is going to apply for quadratics. Now, you're not going to be using y equals mx plus b for quadratics, but you will be using something called vertex form. And that will serve as our variation for the parent graph here, y equals x squared. We'll get into that a little further. Now, for most of the transformations we see here, both linear and quadratic are taking on the exact same format. Whether it's a vertical shift, a reflection, steep incline, low incline when we're talking about linear functions, a slim u versus a wide u when we're talking about quadratic functions, the formats are the same. Difference being we're using x for linear functions and x squared for quadratic functions. One of the only other differences are that linear functions do not have a horizontal shift, but quadratic functions do. And the value is always represented by the number inside of the bracket. So just before we put those transformations to work, I want to share 3 tips to help keep us on track. So starting with translations. We're going to translate your parabola as if it were a closed figure. So take yourself back to elementary school days where your teacher would give you a triangle, let's say, ask you to translate the triangle 2 units to the right and 2 units up. Then your triangle, the entire thing, would be in a new spot, right? So use that same mentality when you're doing any vertical or horizontal shifts of your parabola. Also, it's important to start with your parent graph. Always sketch your parent graph. Y equals x squared. Super important. And you should know the first 5 coordinates of that parent graph. So that's from -2 right through to +2. Okay? So for our first transformation, we have y equals x squared, which is our parent graph, and it becomes y equals x squared plus 2. So what does that mean? It means that we are going to have a vertical shift up 2 units. We'll be shifting the entire parabola as if it were a closed figure up 2 units on our graph. What does that look like to us? First, let's sketch our parent graph here, and then shift the entire graph up 2 units. So what does that look like? This is our new graph. Now it's important to note as well that for vertical shifts, it's never a value that you find inside of a bracket. So just keep that in mind when you're looking at vertical versus horizontal shifts. So example number 2, we are going to be graphing y equals bracket x minus 2 close bracket squared, always using your parent graph as a reference point. So 2 things to note here. First things first, it is going to be a horizontal shift. Why? Because the value is found inside of the bracket. Second thing to note, if the value inside of the bracket is negative, you move right. If the value inside of the bracket is positive, you move left. So you're always using the opposite value there. So in this case, we're moving our entire parabola as if it was a closed figure 2 units to the right. Let's see what that looks like when we sketch it. Always starting with our parent graph and then shifting the entire parabola 2 units to the right. So example number 3, this time we're transforming our parent graph into y equals negative x squared. So as soon as we have that negative x squared, we know for certain that it's going to be a reflection about the x-axis. Let's see what that looks like. First we sketch our parent graph, and then we use the x-axis as a sort of mirror to find the new positioning of our new graph. So let's keep things moving here. Example number 4, we're going from our parent graph to y equals 2x squared. So what we need to remember here is that any coefficient that is greater than 1 will always indicate a stretch or a slim graph, okay? A slim U shape, as we previously said. So this is going to be a stretch by a factor of 2. That's the technical way of saying it, but I just like calling it a slim U. You're going to see what I mean. It's going to be a little bit skinnier than our parent graph because we're stretching it by a factor of 2. In example number 5, we are transforming our parent graph y equals x squared into y equals 1/2 x squared. So the easiest way to remember that any value, or any coefficient rather, less than 1 will give you a wider graph is to say fat fraction. So usually wherever you see a fraction or a decimal, say fat fraction and know that your graph will be compressed. That's the technical term. It'll be compressed by a factor of 1/2. Let's see what it looks like on the actual graph when we sketch it. Parent graph always goes in first, and then our transformed graph is just a tad bit wider than the original. Example number 6. Let's put it all together now. So y equals x squared, parent graph, new graph, y equals -2 bracket x plus 2 close bracket squared plus 3. Now, the easiest thing for us to do is to work through each of the transformations one at a time. You always start by sketching your parent graph and then, put together a list of all the transformations. Reading the equation from left to right. So just reading it, y equals negative. Negative indicates a reflection about the x-axis, but I find that to be the easiest transformation. I just do that one last. After the negative, we have the number 2. So that acts as our coefficient. Remember, we have a coefficient that's either greater than 1 or less than 1. In this case, 2 is greater than 1, which will make for a slimmer u. So that's a stretch by a factor of 2. After the 2, we have the values inside of the bracket. Any values inside of the bracket make for a horizontal shift. A horizontal shift with the opposite value or the opposite direction than the one that's indicated. So here we have positive 2, which means that we are going to shift our parabola 2 units left, negative 2. Okay, on the outside of the bracket, we have a positive 3. That always indicates a vertical shift. And in this case, it's going to be 3 units up. I'm going to conduct both the 2 units left and the 3 units up in one step. Here's the new positioning of our parabola. Now I go back to the beginning and do that reflection. Now the lowest point on our parabola is at negative 2 and positive 3. I just pin down my pencil there and flip the parabola upside down. And this is the result that we have. Here is the final parabola, or the parabola that represents y equals negative 2 bracket x plus 2 close bracket squared plus 3. Now, it's important to note that we have something called mapping notation, and it's a great way to find the new coordinates of your graph when there are multiple transformations, and you can do it pretty much in 2 steps by using algebra. I'll have another video that goes over the mapping notation as well. Here are your skills to succeed. So know the parent graph. I can't stress this enough. This is the starting point. This is your reference point. Once you know the parent graph really, really well, you remember all 5 possible transformations for a quadratic function. And lastly, but definitely not least, make sure that you list your transformations and you carry them out one transformation at a time. And just like that, you've become a master of quadratic transformations. Thanks for watching.